Good morning, everyone. As usual, how did the homework go? Please put your question on chat while everybody join in. So get going. So we're talking about sequences, and a sequence is crucial to know that it's nothing more than a list of numbers. Just a list. A list. Nothing more than that. And we denote it by AN. So it's a list of numbers. And what we care about is when n becomes very large, this list, what happened to it? What happened to the term an when n is very large? That's what we care about. So we look at two problems, number 22 and number 31. 22. Right. So we have the following sequence. K over the square root of 9k squared plus 1. Okay, so that's here my sequence. It means the general term is k over the square root of 9k squared plus 1. So that's really the general term. So we're looking at a bunch of terms, a lot of them. So if k is 1, so that is the pattern is not a great pattern, but if k is 1, so it means we're looking at, so k is 1 over the square root of 9 plus 1, which is 10. If k is 2, we're looking at 2 over the square root of 9 times 4, 36, 37. That's really this list. And let us say 3 over the square root of 9 times 9, which is 81 plus 1, which is 82, and so on and so forth. So that's a list that we're looking at. The question is, as you move forward in this list, those terms here, do they get close to something specific, or they actually blows up to infinity, or they oscillate? What happened to them? So what we need to find is what happened when k goes to infinity to this term. And we're going to do it algebraically. Means when I start putting large k's, k equal 100, k equal 1,000, what happened to this ratio right there? Right. So to find the limit, we use exactly what we've learned in Calculus 1 and basically in Calculus 1. We analyze it first. So when k goes to infinity, this goes to infinity, becomes very large, and this really becomes very large. Okay, so we have a large number over a large number, and we know that in this case, it's indeterminate. So we have really to manipulate to be able to get. All right, one way to manipulate is we've learned L'Hopital's rule. Now, if you try L'Hopital's rule here in this problem, we're going to have an issue. It means it's going to somehow, so I'll do it on a separate side because let us say I didn't think hard and I applied L'Hopital's rule. I'm going to show you the difficulties that we're going to have. Suppose I do it. The numerator is going to go 1. That's the derivative of the numerator. The derivative of the denominator is 9k squared plus 1 to the power a half. So it's going to be a half times 9k squared plus 1 to the minus a half times the derivative of the inside. So this is minus a half, so this is going to go up here because it's minus. 2 and 18 will give me 9k. So when k goes to infinity, what's going to happen? This will go to infinity and this will go to infinity. If you try L'Hopital's rule again, for those who tried it, you're going to realize that you're going to be in a loop. You're never getting out of it. If I try it again, look what happened. This will be 9. And this will be basically 18k divided by that. If you do the derivation completely, it means if you find the derivative, that's what you get. What do you think is happening? So I applied L'Hopital's rule again, I ended up here. I applied again, I end up here. What's really, and if I do the math, this is 9 here. So it's going to give me 18k over 9k squared plus 1 and bunch of constant. What do you think is happening now? The radical is just switching the denominator to numerator and back again, exactly. So whatever I do, first here, I just switch radical k. I switch k, the radical. So I'm really looping. I'm not getting out of it. L'Hopital's rule is not getting me anywhere in this problem. L'Hopital's rule has to be scratched. So sometimes the L'Hopital's rule itself doesn't get me anywhere. So we have to think differently to find the limit, algebraic. So equal. Who has an idea how to do that? Any idea? You can rewrite to include everything under the square root, and she is absolutely correct. The trick to do that is the following. Watch what the trick is. K, we're going to rewrite it. So I have a square root. I would like to basically manipulate a little bit. I'm going to rewrite it as this one, which is absolutely correct because K is the square root of K squared. So this will become the limit. As K goes to infinity, now I can put the whole thing under the same square root. Now at this stage, I said do the following. This is infinity over infinity, but I know how to do this piece. I can divide by K squared both sides. So here we're going to divide by K squared, numerator and denominator. So if we do that, we will get the limit as K goes to infinity of. I divide the numerator, I get a 1. I divide the denominator, I get a 9 plus 1 over K squared. So what we did is we divided this by K squared, we divided this term by K squared, everything. So we're not really changing the value, we're just manipulating. And now we're done. When K becomes very large, 1 over K squared will go to 0. And then I will have the square root of 1 over 9, which is a third. Okay, so that's really the type of the limit we're going to do that. Okay, so L'Hopital's rule got me nowhere, which was our first attempt. So we have to manipulate in a different format.
I have 2 questions real quick.
Yeah.
First one is, so this all happens because of the square root on the denominator?
That's what caused it, yeah.
Okay. So, and one more question.
Sure.
Do we have to do it algebraically, or could we do it like the graph way?
Absolutely, algebraically. You will be forced, yeah, you will have to do it algebraic. You can use the graph to check your answer.
Okay.
All right, algebraically, not numerically. And if you do it numerically, you can do it numerically if you want. It means just plug in large numbers and you will see you're going to get a third. So if I plug in a large number here for K, so let me plug in 1,000 since I have a calculator, why not? And I divide it by the square root of 9 times 1,000 squared, and let's see, plus 1. Let's say I do that. I'm getting almost 0.3333, which is a third. So that's really what we're doing. We're asking ourselves what happened for K large, but we will have to do it algebraically. Okay, so you will be required to do the same work I am doing.
All right. Thank you.
Now let's look at your other problems. Let me look at number 31. And what this is, 31. I didn't know I signed this one. Okay, so this is my sequence here. And the question, so my general term has the form 3 to the n plus 1 plus 3 over 3 to the n. Okay, and the question again, what happened when n goes to infinity? Again, we need to find the limit as n goes to infinity of this expression. All right. Again, what happens when n goes to infinity? So when n becomes very large, you have a number 3 raised to a larger and larger power. So this numerator will go to infinity and the denominator also will go to infinity. All right, how do you guys want me to find the limit? Any ideas? Okay, those who have their camera on, thank you very much. I would rather see everybody with their camera. Okay, any idea? How shall we compute this limit?
L'Hopital's rule.
L'Hopital's rule. All right, let's try it. L'Hopital's rule is not our friend today. And let me tell you what. Let us suppose I apply L'Hopital's rule and you have to tell me what's the issue here. Okay, it's the limit as n goes to infinity of the derivative here. So we pretend it's in x here. So when we're finding this derivative, we're pretending that this is really in x, not in n. Okay. That's what we're pretending. Now, what's the derivative of 3 to the x? Who remember the rule in general? If you have a to the x, what's the derivative of a to the x? Anybody remember?
Doesn't it have a natural log in it?
Here you are. Very good. It has a natural log in it. What it is? It's not, just remember, this is not x to a power n. So we don't use the power rule. It's ln of a, whoever remembered, very good, it times a to the x. Okay, so remember, this is the rule. It's not x times a to the x minus 1. So here a is a constant. So it's not, the derivative is not x a to the x minus 1. Absolutely wrong. This is not a power function. This is not, that's, a is a constant. It's not x to the power 3. It's basically 3 to the power x. So be very careful right there. All right, so suppose I go ahead and I use it. Let's see what I get. 3 to the n, it means I pretend this is 3 to the x. It's going to be ln of 3 times 3 to the x. Okay, the numerator, 3 to the n plus 1. So basically that's a chain rule here. That's my inside. So it's going to be ln of 3 times 3 to the n plus 1. So this is n times the derivative of n plus 1, which is equal to 1. So I will get that. Actually, it's the L'Hopital is going to work here. So this is going to be equal to what? ln of 3 really cancel each other out. I will have the limit as n tends to infinity of 3 to the n plus 1 over 3 to the n. Okay, back to you. Who can give me this limit? Remember, you guys have to show all the work in those limiting issues. Who can give me the limit now? Who can tell me what to do? Okay, I have a good suggestion here. Anybody else?
The 3n plus 1, you can make it 3n times 3.
Very good. This is equal to the following. 3 to the n plus 1, which is a trick I'm going to use over and over and over, starting, today almost. 3 to the n plus 1 is 3 to the n times 3. We can split it, because if you take 3 to the n times 3, it's 3 to the n plus 1, divided by 3 to the n. Very crucial thing that you will be doing a lot. So 3 to the n plus 1 is 3 to the n times 3, because we just add the power n plus 1. This goes, we get an answer for 3. So that's really the best way to do that, which is equal to 3. Okay. So those are good problems because each one of them is different and we're learning a lot from them. Now I look at number 45. Now another way to do this problem. Who can think of another way to do this problem? Anybody thought about this problem in a different way? Anybody has any other idea how to do it? Split the numerator then. Okay, I'm gonna split the numerator. So your classmate has a good idea. Let's watch how she's doing it. We cannot always do that, but in this problem, you know, math is a lot of time is about looking and see, you know, what I can do with quantity. So that's really an easier way to do it. This will give me the limit as n tends to infinity of 3 to the n plus 1 over 3 to the n. We did it a minute ago. This is going to give me a 3 plus 3 over 3 to the n. And now when n becomes large, 3 to the n goes to infinity. 3 over that will go to 0, which is equal to 3. End of the problem. And the chain of the L'Hopital's rule was not really necessary. So that's a really different way, another way to do the problem that I would like you to be able to do it both ways. And this is much shorter, actually. Okay. All right, so now we look at number 45. And 45. All right. So now we have the following: n over e to the n plus 3n. Okay. And so the terms, the general term of the sequence is n over e to the n plus 3 to the n. And we have to compute the limit of the ratio. And then we have to analyze this thing. All right. Once after we evaluate it, we have to see is our answer makes sense. Okay, so the first step we do always is we analyze what we have. So when n goes to infinity, my numerator goes to infinity. My denominator goes to infinity. So I have large over large, which is definitely indeterminate. We don't know what it is. So this is the perfect scenario for L'Hopital's rule. So it's the limit of the derivative of the numerator over the derivative of the denominator. The derivative here is 1. The derivative here, e to the x. So basically you pretend that this is e to the x plus 3x is e to the x. So e to the n plus derivative of that is 3. Okay. And the question is now this is equal to what? Now n goes to infinity, this is going to go to infinity, becomes very large. 1 over something very, very large is very, very small. The limit is equal to 0. Okay. So now my question to you, do we expect a 0? Should we expect a 0 just by looking at it, and why? Back to you. I want you to think about
because the denominator goes to infinity way faster than the numerator.
Exactly. What's the numerator? And we've talked about that before, but we have to build it up. When n becomes very large, you have e to the n plus 3n. E to the n goes to infinity way, 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 way faster than n. It means even if I put, so if you remember the table, if I put, for example, if I take even n equal to 5, so suppose I take n equal to 5, e to the 5 is equal, so e to the 5 by itself is already very big. So if I take e to the 5, e to the power 5, this is already 148.41. So when I'm going to take the ratio 5 over e to the 5 plus 3 times 5, which is not really important. This is 148 plus something. That's going to be actually a small number. And things get actually worse when I take n equal to 10. I mean, I'm taking very small values of n, but e to the 10 is actually very, very large. So you can see that the ratio is going to be very, very small. So this is already 22,026. So when I'm going to take 10 over that, you're dividing by 22,000. 10 over 22,000, this is going to be very small, actually very close to 0. All right. So in this particular problem, it's still a lot of time. We have to know that the exponential goes to infinity way faster than n. So this is going to cause basically the ratio to become very small because I'm dividing a number by something way, way, way bigger than it. So the ratio is going to be very small. So we should expect 0 in this particular problem. Any other questions before we proceed and finalize this section? Okay. All right, so I'm going to do 2 more examples where I'm going to alternate the term, even though the book doesn't have a lot of problems along those lines, but we have to understand it fully. So I'm going to take two sequences actually. So the first one is, and I touched upon this yesterday, but we're going to do it again today. So find the limit of the following sequence if it exists. Find the limit of the sequences below. So the first sequence is have the 4 minus 1 to the n over n. So this is my sequence. Okay. So the terms are if I start at 1, I will have minus 1, a half, minus a third, a fourth, minus a fifth, and the terms are alternating, positive, negative, and we keep going. And the question is, we need to find what happened when n becomes very large. Over n means the limit as n tends to infinity. I'm going to write the minus 1 over n in front of it and multiply it by 1 over n. What happened to those terms when n become very large? Do you guys remember from yesterday what's going to happen? And why?
Aren't they both reaching 0, both sides?
Yeah, exactly. Watch carefully. I'm going to kind of close my eyes on the minus 1 for a little bit and just focus on this term. So this term goes to 0. So note that when n becomes large, the 1 over n become close to 0. That's really what's happening here. So when I take the term of the series, what's the picture here? If I'm going to graph it, so I'm going to have 1/2. So if n equal 1, it's minus 1 down here, and then it's a half. So that's where the terms are. If we graph them, at 3, I am at minus a third. At 4, I am 1/4, and then I am at a fifth, and then I am at a sixth. As you realize, from both sides, from the negative and the positive, the terms are really getting closer and closer to 0 from both sides, the negative terms and the positive term. So here, all the terms of the series, all the terms of the sequence, whether they are positive or negative, are approaching 0. Whether they are positive or negative are getting close to 0. So the limit in this case is, honest to goodness, 0. Okay, so that's really the reasoning behind that. Whether positive or negative, they are getting close to 0, so the limit will have to be 0. Even though they alternate, but they are getting close to 0 both ways. Now, immediately, we're going to contrast this with the following sequence. So suppose now I take the following sequence. -1 to the n, let us say, and I don't know, n over for n plus 1. That's the sequence I'm going to look at. All right, so let's see how the terms are. I'm going to write the first few terms just to have a feeling for it. So let me assume I'm starting at 1, for example. I will have minus 1 over, let's see here, 1, 4 plus 1, it's a 5. And then it's positive. I will have a 2. It's a 9, and then I will have a 3, and I'm going to have a 13, but it's a minus. So we're really alternating. And then it's a 4, 17, and then and so on and so forth. So the signs are alternating positive, negative. Okay, what is the limit now of that? Okay. All right. Anybody like to pitch in? What's happening here?
I don't think there is a limit.
Because we have to be very clear.
Because both sides are increasing.
I
Like
don't understand what you mean.
like when you divide 1 over 5, it's 0.2. When you divide 3 over 13, it's 0.23. They're both like it's increasing from both sides.
I mean the terms are increasing.
Yes.
Yeah, but why it's divergent?
Yeah, it diverges.
Why? I'm still not getting it. Anybody, please, I want each one to pitch in.
It's not going to a specific like point, I guess. It's not going.
Yeah, where is it going? Can we be a little bit more focused? Slowly, slowly. Anybody, where do you think those terms are getting close to? I mean, not, but what's happening? The picture.
Going to
Going
infinity.
to positive and negative infinity? No, not infinity. Keep looking.
Aren't they both going to 0?
No. Let us analyze. Let me focus on this term, okay? Let me focus on this term by itself. All right, you see I'm dropping the -1 to the n. Okay, we're getting better now. Let me focus on n over 4n plus 1. This piece for a little bit, and then I go back to the -1. It means I'm looking at those terms without the sign. Okay, what's happening to those terms when n becomes very large? Back to you. What's the limit of that when n becomes very large? Can anybody see it? It's 1/4. I'm getting 1/4. Is she correct? Is the limit 1/4? We're going to do it 2 ways, actually. First, when n goes to infinity, this is going to go to infinity over infinity. You can, if you want to apply L'Hopital's rule, and you get the limit 1/4. It means it's 1/4. Okay, so when n goes to infinity, this ratio will become close to 1/4. Or you can actually think about it. When n is large, the numerator is n, the denominator of 4n plus 1. I mean, that's the intuition. This is the work you have to show. You have to show everything. When n is large, the numerator is n. But the denominator is almost, because 1 is very small compared to 4n, so you can think for the denominator is 4n. So it's like having n4 over, which is going to give me 1/4. So intuitively, definitely it's 1/4. And without intuition, we use L'Hopital's rule, we get 1/4. So what is really happening here? So those terms are not blowing up. Those terms are actually becoming close to 1/4. What is the minus plus doing to us? What's this minus? So what's doing is the following. Some of the terms, like -1/5, which is that's A1, and this is A2. So what's going to be the picture? A1 is -1/5. So this is 1. This is -1/5. Right here. This is 2/9. This one minus 3 over 13. Now, when your classmate says that 3 over 13 is bigger than 1 over 5, I mean, he was right, but things are not blowing up. So 1, 2, 3. So this is 1, 2, 3. This is 4. 4 is 4 over 17. And then we're going down. But as they are increasing, what's happening to them? Are they blowing up those terms or not? It means when n is becoming large, are those terms blowing up? What happened to n over 4n plus 1? When n becomes large, they are not blowing up. They are actually becoming close 1 over 4, some of them, and some of them are becoming close to minus 1 over 4. So the term themselves, without the minus, are heading toward 1/4. So the negative 1 will head toward minus 1/4, and the positive 1 are heading toward +4. So it's not blowing up. They are not blowing up. That's really the picture. So now let's see what the picture. So what's happening here? All the ANs, where according to my picture, all the positive ANs, if you want, or the positive AN, so let me write it actually in an easier term, all the positive AN are becoming close to 1/4. And all the negative AN are getting close to minus 1/4. So some terms are getting close to 1/4 and some to minus 1/4. So therefore the limit, the sequence diverges because we don't have a unique limit. Sequence diverges. Okay. But they don't blow up. That's really the picture in here because the terms without the sign are getting close to 1/4. So this is dragging all the positive term toward 1/4, or the negative toward minus 1/4. Or basically the more precise way, all the AN where n is even are going to +1/4. All the AN where n is odd are going to the minus 1/4. And that's really what's happening here. So positive AN or n even. And those are the odd. Okay, so when I have an alternation, when the sign alternate, and then what we have to look at is the terms without the sign. What's happening to them? If those terms goes to 0, then I am in the first picture. The positive and the negative head towards 0. If those terms don't go to 0, when you start alternating the sign, we're going to have some of them going one way and some going the other way. So that's really the general picture for the scenario. These questions before I move on to the last thing I want to talk about in this section. Okay. Before we move on to basically what this chapter is about, which is the idea of infinite sum, there is one more type of sequences that is going to come up with us a lot, and we have to basically get it done. So sequences of the book is calling them geometric sequences. I don't want to use the same word, but the sequences of the form r to the n, where r is a constant. And the book called those sequences geometric sequences. R is a constant. So it means I'm looking at the following sequence, something like that. A constant r, r squared, r cubed, r to the power 4, and so on and so forth. So this is the sequence that I'm looking at. Okay, so I'm going to take different cases, and we're going to elaborate this whole thing by example, and then come up with a general rule. It means those type of sequence where, when do they converge? So suppose I take my r to be, I don't know, something like 0.8. Okay, this is my r. So it means that the sequence I'm looking at is the following: 1, 0.8, 0.8 to the power 2, 0.8 to the power 3, etc. That's really what I am looking at, 0.8 to a power. What happened to those terms when n becomes very large? Anybody have any idea? Anybody? When n becomes large, what happened to those terms? Do they become large? Do they become small? Well, I don't know.
Small. They
Anyone?
become smaller.
You think it becomes smaller because? So at 1, we are at 1. Then at 2, it's 0.8. So this is, so anybody can justify why they are getting smaller. Because it's crucial. Those are important to know. Why they are getting smaller? Usually the rule is when you take a number less than 1, and you raise it to higher and higher power, the number actually goes to 0. But mathematically, what's happening? This is 0.8. Now, and then this is 3, this is 2, 0.8 to the power 2. Now, which number is smaller, 0.8 or 0.8 square? Which one is smaller?
0.8 squared.
0.8 squared, because 0.8 squared, one way to look at it, is 0.8 times 0.8, right? Big deal. So you're taking 0.8 and you're multiplying it by something which is less than 1. So multiplying a number by something less than 1, this is going to make it definitely smaller. So 0.8 to the power 2 is going to be smaller than less than 0.8 because you're multiplying by a number less than 1. What about 0.8 to the power 3? I mean, the picture is showing it smaller. Is it smaller than 0.8 to the power 2? And the answer is for the same reason. 0.8 to the power 3, you're basically taking the previous number and you're multiplying it by 0.8. So every time you're multiplying the term before it by 0.8. But this number you're multiplying it by is less than 1, which is causing the term actually to keep decreasing. So every time you move, the term actually are getting smaller and smaller because they are decreasing. You're multiplying them by a number less than 1 and smaller. And they never stop getting smaller. They never stop becoming smaller because you're multiplying them every time by a number less than 1. So 0.8 to the power 4 is 0.8 times 0.8 to the power 3. So the numbers are really getting smaller and smaller and smaller. So when you take a number which is less than 1, you start raising it to a higher and higher power, the number gets smaller and smaller and smaller. So in this case, the limit of those terms is going to be equal to 0. So a rule of thumb, and that's really the explanation of the rule, is that you're multiplying from here to here, you're multiplying by 0.8, which is less than 1. Again, you're multiplying by 0.8, which is less than 1. So the numbers are actually decreasing. And they never stop. That's why they go to 0. So if a number is less than 1, you raise to a higher power, it becomes very small. What if I take minus 0.8? Will the picture be the same? What do you think? (0.8 square minus 0.8 cube, etc., etc. Because when I multiply what's in minus, when I start raising it to the power, first to the power 0, I get 1. To the power 1, it's a minus. To the power 2, I get the plus. To the power 3, I get a minus. What do you think this limit is going to be?
I think it's going to diverge.
Why?
Because since there's negatives, it's going to go different sides.
Why?
because every positive is going a different way and every negative is going a
Every
different
positive is going where? All of you. The positive are going where?
Towards
What?
0.
Towards 0. It's 1. 0.08 square. 0.8 to the power 4. This is again the number, which is less than 1. So 0.8 square, 0.8 to the power 4. The number are getting smaller. 0.8 to the power 6. So all the positive are heading towards 0. All the negative are heading towards 0. The whole sequence is going to head towards 0. Okay, because the terms by themselves are not blowing up. The terms without the sign, so if you remove the sign a little bit mentally, those terms, you're taking 0.8, which is a number less than 1, you raise it to a higher power, the number is getting smaller. The terms without the sign are heading toward the 0. So even if you put the sign back in, they're still heading towards 0 from both sides, positive and negative. So now the picture would be a 1 minus 0.8, 0.8 square, minus 0.8 cube, 0.84, minus, plus, minus, plus, but we're heading towards 0 from both sides. We're back again to the following, the same scenario. So this gives me that the limit. If you have minus 0.8 to the power n, this is equal to 0. And the reason is that this 0.8 here is a number less than 1. So the 0.8 are heading towards 0. The minus will make them hover around 0 from positive and negative. Now, what if I take another number? So this is the first picture. So what's important is when you take a number less than 1 and you start raising it to higher power, you're making it smaller because you're multiplying it by a number less than 1 every time. Now, what happens if r is bigger than 1? And then we come up with our rule. Okay, so suppose I take r to be, let us say, I don't know, 1.1. It means I'm looking at the following scenario. 1, 1.1, 1.1 square, 1.1 to the power 3, etc., etc. Okay. Now what happened here? When n becomes large, do the terms become larger or smaller? So this
Larger.
is larger. Absolutely, because this time you're multiplying by what? 1.1 square means I take the previous one multiplied by 1.1, which is bigger than 1. When you multiply something by a number bigger than 1, you make it larger. 1.1 to the power 3. I'm multiplying the previous one by a number bigger than 1. So from here to here, I am multiplying by 1.1. So I'm making my number larger. From here to here, I'm multiplying by 1.1. I'm making my number larger. So every time I'm making my numbers larger and larger. So if we draw the picture, we're gonna go like that. And I never stop making them larger. So the terms are gonna blow up. So in this case, the limit is gonna be equal to infinity. Okay? Because every time I'm multiplying by a number which is bigger than 1. And finally, if I take minus 1.1, what's going to be the picture?
Alternating symbols.
Alternating. Now let's be very more precise as we did.
So 1, negative 1.1, 1.1 squared, negative 1.1 cubed.
Okay.
Well, whatever the answer of 1.1 cubed is.
I'm not going to compute it. Forget it. Then minus. So how, if we graph it, how the graph would look like? How do you think the term will do? So if I draw A1, A2, A3, how do you think the picture will be?
Would it not diverge to both in positive infinity and negative infinity?
It will not diverge. Be very precise. All of you, please. How's the picture look like? Do you have any idea? That's what's happening in this scenario. So this is gonna be 1, 1. This is 1, 1.1, 1, 1.1 square. What's the picture is going to be here? It will diverge to minus and plus infinity. It will diverge, not to minus and plus, and it will diverge because, let's see what your classmate is telling you. This is the first term. The second is minus 1.1. The third is 1.1 squared, which is larger than 1. It's going to be here. This one is going to be down here. And then this here. So what's going to happen here? The positive terms are going to go to plus infinity. The negative term are going to go to minus infinity. That's really what here the picture. So what's going to happen here? So 1.1 square, 1.1 cube, those are going to go to plus infinity. The others will go to minus infinity. The sequence doesn't go to plus infinity. Even here, the sequence diverges, period. The sequence will diverge. And the reason is all the terms, all the positive terms, so this is alternating. All the positive terms go to plus infinity and all the negative terms are going to minus infinity. The sequence will diverge pure and simple. So let me summarize the behavior of those particular sequence. So if we consider the sequence, so R to the n or 1R, those type of sequences. So just bunch of numbers. Then, what do you think gonna be the rule? When those sequences will converge? So when those sequences will converge? Under what condition on R will the sequence converge? Anybody like to give me the rule? If R is less than 1, an absolute value, whether it's less than 1 here or less than 1 here. So if the number R is less than 1, the sequence will converge and will converge to 0. So the rule is going to be if R is less than 1 in absolute value, whether it's positive or negative, then the sequence converge and the limit is equal to 0. So if this number less than 1, now, if R is bigger than 1, like 1.1, then it diverges, and it diverges, the limit is plus infinity. So definitely diverges. If R is less than minus 1, then we have alternate. The limit just purely diverges. Then the sequence diverges. Okay. In this case, it diverges, but its behavior is it's going to blow up. When R is less than minus 1, it purely diverges. So those geometric sequence that the book is calling have the following behavior. 1R. If R is less than 1, an absolute value, it will converge to 0. Otherwise, it will diverge. So let us may have 3 typical examples. So let me take the following. Decide whether the following sequence converge or diverge. So the sequence. 3/4 to the power n. Does the sequence converge or diverge? So basically I'm talking, I will write it in terms. So basically I'm talking about the following fifth sequence. 3/4, 3/4 square. That's really what I am talking about. Okay, so does the sequence converge or diverge quickly?
It converges
To where?
0.
And right.
And because the number is less than 1, the
Right. R,
coefficient.
exactly. R is 3/4, means 0.75. What I'm doing is I'm taking 0.75, 0.75 squared, and so on and so forth. This is equal to 0 because R here is 3/4 and R is less than 1. Okay, so this type of behavior, we have to know it immediately. All right, let's take 2 more quick example. Suppose I give you the following. Let us say -1 to the n times 0.3 to the n. So that's example number 2. Does this one converge or diverge? And can we see in this the type of behavior that I am talking about? So let me start from 1 to infinity. So, okay. So that's 0.3, just to get that straight. Okay, ideas? Converge, diverge, what's the behavior?
Converges to 0 again from
Yes,
both the
because.
positive and because whenever I see -1 to the n, it just what you said before, that it just flip-flop symbols, negative and positive, but it also for the absolute value of R, it'd just be 0.3, so it's converging
To where?
to 0.
To 0. The -1 to the n, you're right. It flipped the sign. But the 0.3 to the n makes it go to 0. Because 0.3 is less than 1 makes it go to 0. So I'm just going to force the whole thing to go to 0. Or in another way, you can write this as the follow. This is basically minus 0.3 to the power n. And here my r is minus 0.3. It means this is less than 1. So this limit is going to be equal to 0. Okay, so -1 to the n, make it go up and down, but the terms are heading towards 0 because 0.3 is a number less than 1. When you take it to a larger power, the numbers actually shrink because it's less than 1. All right, my last example before we finish. Suppose I take the following sequence. Which looks slightly different from the previous behavior, but what is going to be the limit? Do not try to use L'Hopital's rule because it will put you in a loop. So how can I use the ideas we've developed to find the limit of that? Anybody?
Can we just rewrite it as 4n times 5n plus 1 to the negative power?
We can, but why would this help me?
I just thought of it as just getting you to a familiar look.
Yeah, but usually we rewrite what you said was 100% correct to improve, to help me more. Rewriting it this way will not reach in this particular problem, will not move me forward.
All right.
Okay, so what do you think will move me forward here? I'm going to split that as 5 to the n times 5. Am I correct? Are those two the same?
Yeah.
Now, why did I do that? Quickly.
So you can
Plus
divide
1.
by that.
What?
Can you make 4 over 5 to the n power just itself?
Absolutely. And then it's not I'm forgetting about the 5. Of course, I don't. 1 over 5. And what's the benefit of doing this? What's the benefit of doing that? This term here. What happened to it as n goes to infinity?
It converges to 0.
Right, limit as n tends to infinity of 4 over 5 to the power n is equal to 0 because 4 over 5 is less than 1. It's 0.9. Take 0.9, start raising it to a 0.8, sorry. Take 0.8, raise it to a larger and larger power. You're gonna get, the number is gonna get smaller and smaller. This is gonna become close to 0 times 1 over 5 is going to be equal to 0. Okay, so the reason I did what I did is basically to actually rewrite it in a format that I can recognize. All right, so for tomorrow, basically, for those who didn't, I just added 2 problems. And for those who didn't finish your homework, please do your homework because we're going to switch tomorrow to what we mean by infinite sum. So I want idea of limit to be down quite well. Okay. All right, class is dismissed. As usual, anyone with questions, you can stay.